we'll continue on here, and if you think about what we did with confidence intervals. Okay, so we had confidence interval for mu1 minus mu2, and we came to the conclusion, it ended up being y bar 1 minus y bar 2 plus or minus t star times the standard error, s1 squared over n1 plus s2 squared over n2. Okay? And we said if 0 is in the interval, then we have evidence that mu1 does not equal mu2, right? That the means are different, okay? And I'm sorry, did I say is in the interval? Okay, then I'm sorry. If 0 is in the interval, then we do not have evidence, okay? We do not have evidence that they are different, okay? Then we do not. Okay, and if 0 is not in the interval, then we do have evidence that mu1 does not equal mu2. Okay? And notice I don't say we have evidence that mu1 and mu2 are equal. We just say we do not have evidence that they are different. Okay? Similarly, let's say we have a t-test, independent samples. Okay? Our null hypothesis is that they, mu1 is equal to mu2, and the alternative is that they are different. Okay? And then, we calculate a test statistic. Test statistic t equal to y bar 1 minus y bar 2. Basically minus 0. I don't know if I have to actually subtract off the minus 0. Divided by s1 squared over n1 plus s2 squared over n2. Okay, and we can see that actually they're like like the same elements. Same elements appear in both of these things. Okay, and the conclusion is that if the p-value ends up being less than alpha, we reject the null and conclude that we have evidence that mu1 does not equal mu2. And on the other hand, if the p-value ends up greater than alpha, we do not reject the null hypothesis. Okay, and we do not conclude, or we conclude that we do not have evidence that mu1 is different from mu2. Okay, is this okay? So effectively, we're doing kind of similar things. We're asking, do the populations, population 1, population 2, do they have the same mean, or are they different? Okay. or do we have evidence that the means are different or not? Okay. And so there's a close relationship between t-tests, especially for independent samples, and confidence intervals. And in fact, kind of the results are almost interchangeable. All right. So if I may, I'm going to flip to the next slide here. Or it looks like some of you guys are still writing. Okay. And so, so let's say you perform a t-test with alpha equal to 0.05. Okay? The conclusions from this t-test about mu1 and mu2 will match the conclusions that come from a 95% confidence interval. Okay? Okay. So meaning, so if in your test, if you're well, okay, so let's say, so if you conclude that mu1 is not equal to mu2, okay, that means your p-value was bigger or smaller than alpha. We've come to conclude that mu1 and mu2 are different. Yeah, it means that our p-value was less than alpha. Okay, it means that p-value was less than alpha, and we rejected the null hypothesis. Okay. Similarly, so a 95% confidence interval would come to the same conclusion. Okay, so if we made a 95% confidence interval, would 0 be in the interval or not? Yeah, and the answer here would be no. Okay, 0 would be outside because we would come to the same conclusion, which leads us to the conclusion that mu1 is different from mu2. All right, here's a question. Let's say I redid the exact same test, okay? Same data, same test, okay? This time, alpha is equal to 10%. Is my p-value less than alpha? So up here, what do we know? We said we performed a t-test with alpha equal to 0.05, and if we conclude that mu1 is not equal to mu2, then that means our p-value was less than alpha. Okay? So same data, same test. So effectively, this means that our p-value is the same as in the previous test. So p-value is the same as the previous test. Okay, because the p-value just depends on the data. All right. And so in the previous test was our p-value we know is less than 0.05. Okay, so from the previous test, we know the p-value is less than 0.05. Okay, so we know that for this test, our p-value is less than alpha. Okay, so with alpha equal to 0.10, 0.10, we know that our p-value is less than alpha. Okay, and then that would lead us to still reject the null hypothesis. Is that okay? All right. If I had changed alpha to 1%, what would we now say? Yeah, now we don't know. We don't know. Okay, if our so let's say so t-test with alpha equal to 0.05, we conclude to reject null hypothesis. Okay, if we redid the test, if we test with the same data, but this time, but with alpha equal to 0.01, what do we conclude? Okay. Well, actually, the answer is we don't know. Okay. We do not know if we will reject or not reject. Okay. We know our p-value is less than alpha. I'm sorry, we know our p-value is less than 0.5. P-value is less than 0.05 because from the first sentence, or from the first line. But we do not know if it is less than 0.01 or not. Okay, so we do know that our p-value is less than 0.05, but we don't know if it's less than 0.01 or not. Is that okay? Or is this? Okay. And so again, all of this, so a t-test with alpha equal to 5% corresponds to a 95% confidence interval. Okay, and a t-test with alpha equal to 10% would correspond to a 90% confidence interval. And a t-test with alpha equal to 1% would correspond to what? 99% confidence interval. Okay. I hope this is okay. Yeah. All right. We're missing a lot of students today, huh? Feels very quiet. All right. Okay, so continuing on here, we have, let me talk about directional t-tests. Okay. And so with directional t-tests, we are curious if we want to know if one population has a mean that is larger than the other population. We want to know if there's evidence show that one population mean greater than the other. Okay. And we are not interested if it turned out to be less. Okay, so we are not interested if it turns out to be less. Okay, so or turns out to be the other way around. Okay, so for example, perhaps a company claims that users of their product have more whatever than users of the other competitor's product. Okay, so you know, some we'll say company A claims their users have more I don't know, battery life than we'll say brand B. Okay? And so in this case, we want to know, so we're going to have sample 1, which will be company A, and sample 2, which will be brand B. Okay? And in this case, our null hypothesis always has an equal sign. So the null hypothesis will be that mu1 is equal to mu2. Okay? And then the alternative, or I'll just call this, it probably makes sense just to use A and B. So we'll say mu of A is equal to mu of B. And then the alternative is that mu of A is greater than mu of B. Okay? And if the data shows the other way, then that's we won't be able to support their claim. Okay? So so the test is conducted almost the same way, but before you begin the test, you should check directionality. So before we begin, we check directionality. Okay, and what we mean by that is we just check to see if the data we have even could possibly support the alternative, okay? Does our data support the alternative? Okay, and so let's say we get 10 from group A and 10 from group B, and we'll say y bar of group A is I don't know, 550, and y bar of group B is 600. Okay? All right. If this were the case, if our average of group A was 550 and the average of group B was 600, our data does not support this notion, because we would expect if we're trying to support the alternative, we need y bar A to be more than y bar B. We need the battery life of company A to be more than the battery life of company B. Okay, and that's not the case if this is the case. All right, if this is our data. So if this is our data, okay, we have no evidence to support the alternative hypothesis. Okay, so so here automatically we would not reject the null. Okay, so just automatically conclude, do not reject the null, no evidence to support the alternative. Okay, and our p-value, anytime you just straight off the bat reject a a directional alternative because the data doesn't support that, right off the bat you can say your p-value is greater than 50%. Okay. But if this is what we have, we would just automatically conclude, don't reject the null, and we have no evidence to support the alternative. Okay. So you should anytime there's a directional alternative, you should just kind of do it. This is almost like a common sense check, right? It's just kind of like, if company A is claiming that their batteries last longer or whatever, and when we gathered the data, it shows that their batteries last less, we're not going to have any evidence to support that claim, right? Okay. On the other hand, if it works out, okay, so mu1 again always has an equal sign, so we'll say mu of A is equal to mu of B, and the alternative is that mu of A is greater than mu of B, all right? And then let's say sample A and sample B. We have 10 and 10, and so this time y bar A is, we'll say 550, and y bar B is 500, then our directionality check passes. Okay, we pass our directionality check. Let's say okay, so so here we pass the directionality check. We pass the directionality check because y bar A is greater than y bar B, which is what we expect if the alternative is mu A is greater than mu B. Okay, all right, and then so at this point we would carry on with the hypothesis test, the t-test, okay? And so we would try to calculate a test statistic to get a p-value. And so what would our test statistic would be y bar 1 minus y bar 2 divided by our standard error. So we have 550 minus 500. We're observing a difference of 50, I guess, minutes or 50 points. And we want to know, is that large compared to our standard error? So our standard error would be S1 squared over N1 plus S2 squared over N2. We have 60 squared over 10 plus 60 squared over 10. Okay, we get 26.83. So I get a difference of 50, and I divide that by that, and I get a test statistic of 1.863. Okay. I would look this up with degrees of freedom equal to N1 plus N2 minus 2, so I have 18 degrees of freedom. Okay, I go to my t-table, and I go to the row 18 degrees of freedom, and I want to see where this value 1.863 fits. Okay, so in the row 18 degrees of freedom, I see values like 1.734, I see 1.855, and 2.007. Okay, this is 0.05, 0.04, and 0.03. Okay, so 1.863 fits in between here and here. Okay, which means our corresponding tail must be in between 0.04 and 0.03. Okay, with the other test, with the directional non-directional test, we would look at both tails, but because it's directional, we're only going to look at one side. So we have 1.863, so I only want to look on the side that's greater, because that point's greater. And so I get this tail area is between 0.03 and 0.04. Okay. And so for a one-tailed test or a one-sided test or a directional test, we take our tail probability, and that becomes our p-value. Okay, we don't double it. For a non-directional test, we double the tail area for our p-value. For a directional test, we do not double. So in our case, our p-value is between 0.03 and 0.04. Is that okay? All right? And so if our p-value is between 0.03 and 0.04, and let's say our alpha, we decided to use a 5% alpha, what is the conclusion we make? Our p-value is less than alpha. Okay. So our p-value is less than alpha means we feel like our p-value is small. Okay. Okay, and when we say our p-value is small, this means that we do not think our data was a result of random chance alone. Okay, that it is too unlikely for it to have been a result of random chance alone. Okay, so our data is too unlikely to have happened from random chance alone. Okay, and so we would reject the null hypothesis. Okay, and we say that 50-minute difference we observed between the average battery life of group A and group B was not a result of random chance, but was in fact evidence that brand A's batteries, or company A's batteries, last longer than brand B's. Okay, so we reject the null hypothesis. Okay, we say we have evidence that the average battery life of company A is greater than that of brand B. Is this okay? All right, so that's one-sided tests. Okay. Okay. I'm going to cover, I'm going to jump ahead to cover one section in Chapter 8, okay? And so, you know, we're going to cover a couple things a little bit out of order. I'm going to leave some stuff up for reading. I would say Section 7.6, I think, is a good section to read through. And so, you know, do your reading, you know, and then Section 7.6 is just a little bit more more conceptual stuff, but good. Talking about statistical significance versus importance. Yeah, I don't know what else I have to say at this point right now. Okay, so I'm going to jump ahead, and we'll come back and finish off one section from Chapter 7 next week. But I'm going to cover one section in Chapter 8. So Chapter 8, Section 2. Okay, and this is on the t-test for paired data. Yes. Okay. Chapter 8, Section 2. This is on paired data. And the idea here is the regular old t-test is for two independent samples, sample 1 and sample 2. The individuals in those samples, they have no idea who each other are, or they just have nothing to do with each other. You got sample 1 from population 1 independently from sample 2 from population 2. Okay? In the paired data test, your sample 1 and sample 2 are linked together. Or really, you can think of it almost as like one sample where you kind of have two measurements that you're kind of comparing them against. So your two samples have are paired to each other. Okay, so the two samples are linked. Okay, so probably the most common example is before and after study. Okay, so maybe you have 10 individuals, and each individual has a before and an after measurement. Okay, we want to take into account the fact that these measurements are linked, and we don't want to treat them as independent samples. Okay, or you could have quote-unquote twin studies. Okay, where you get like twins, and you give one twin a certain treatment, and then the other twin a different treatment, and you try to see if there's a difference between them. Okay, you want to take into account that the twins prior to the study were very similar. Okay. Okay. Or other just kind of matched pair studies, where maybe you don't have twins. Okay, but maybe every single person in sample 1, you have found a matching person in sample 2. Maybe just they're of similar age, similar whatever other different characteristics. You're trying to match them up so people are similar, similar height, weight, build, whatever. If you're doing some kind of study on health effects, you want to make sure that they're matched, and so you can see if this person ended up being different from this person or something like that. Okay, so these are paired data tests. So one key thing is that in paired data tests, your two samples will have to be the same sample size. So if you have sample 1 is a different size from sample 2, it cannot be a paired data study. Okay, so sample 1 and sample 2 must have the same number of observations. Okay, but just because they have the same sample size doesn't mean they're paired data. But that's a key indicator that it's not paired data if you end up getting two different sample sizes. Okay, and so here we handle the study a little bit differently. Okay, so let's say does some weight loss pill work? This is our quiz, okay, our question. All right, so we have people. We have Adam, Bob, Carl, Doug, Eric. All right. All right. So we'll have before weights and then after. Okay, so let's say before Adam weighed 265, and after taking the pill, he's down to 260. And Bob weighed 210, and after weighs 205. And Carl was, I don't know, 315, and after is down to 309. Doug was 240, and after is down to 235, and Eric was 195 and is now down to 190. Okay. If we did a regular old, let me get the mean and the standard deviation of these things. Okay, so I'll just punch. Is this starting up? Okay. So I'm going to calculate the mean and standard deviation of these values as soon as my R boots up. Okay, so let's see. Okay, so we'll have before will be 265, 210, 315, 240, and 195. Okay, and then the after will be 260, 205, 309, 235, 190. Okay, so the mean of before is 245, and the standard deviation is 47.56. What is it? 0.566. Okay. All right. The mean of after is 239.8. And the standard deviation of after is 47.199. Okay. Now, if I treated this as an independent t-test, so this is the wrong way to do it, would be to treat this as an independent test, which would be mu1 is equal to mu2 is my null hypothesis, and the alternative would be that mu1 does not equal mu2. Or maybe, in this case, we would want to know that before, we would expect before to be greater than the after. Okay, so this would be the alternative, right? Does some weight loss pill work? You know, we expect the before to be greater than after. Okay. So this would what we would expect to see. We would do our test statistic, which is going to be y bar 1 minus y bar 2 over basically our standard error, s1 squared over n1 plus s2 squared over n2, and we would get, I don't know, something. I could just do t-test b and after. Okay. And this actually does it nice and easy for us. But I'll show you. So we would have 245 minus 239.8 divided by our standard error, which is going to be 47.566 squared over 5 plus 47.199 squared over 5. Okay, so let's see what this turns out to be. 47.566 squared over 5. Huh? Wait a second. 47.566 squared divided by 5 plus 47.199 squared divided by 5. And the square root of that, 29.968. So I have 245 minus 239.8 divided by 29.968. Okay, and then so the numerator, 245 minus 239.8 divided by this number here. I get a test statistic t equal to 0.17. Is that okay? Okay, and so this value ends up being only 0.17 standard deviations away from 0. Okay, and so if I look at this, you know, I'm at 0.17 and I want to know what's the area over here. Okay, I can go to the tests t table, and if I go to the t table, I would have 8 degrees of freedom, and the very first value I see is 0.889. So at 8 degrees of freedom, the very first value is 0.889, and then the next value is 1.397, and this is from our t table. Okay, and so we see, you know, we're only 0.17 standard deviations away. 0.17 is over here, which means my corresponding tail area has to be over here, greater than 0.2. So this area, I don't know exactly what it is, but according to the t table, this tail area is greater than 20%. Is that okay? Greater than 20% and also less than 50%, okay? Because from our picture we can see that it's going to be less than 50%, but we know it's more than 20%, okay? It's probably close to like 40% or something, okay? So at this point we would say our p-value is greater than alpha if we used alpha as 5%, okay? Just our kind of default alpha, or you know, our p-value, you know, let's assume alpha is 5%. Our p-value is going to be greater than alpha, and what would that lead us to conclude? We do not reject the null, and we say we do not have evidence that the weight loss pill works. Is that okay? I apologize that I kind of wrote in this backwards order here, or looping around. All right, but this is the wrong way to do it. Okay, this is treating it as an independent sample. Okay, and so again, with the test, I should actually do alt is equal to greater. Okay, and so we can I don't know if you guys can see, but basically I fed it in the data, the before and the after, and the test statistic t is equal to 0.17. This matches what we have here. Okay, degrees of freedom is very close to 8. We used the approximation of 8, and they're calculating something a little bit else, and they're getting a p-value of 43%. Okay, and then our alternative is that the true difference between in means is greater than 0. Yes?
Why is the upper interval for an 85% confidence interval
Because it's this is they're creating a one-sided confidence interval. So it goes from, basically they're saying I'm 95% confident that the true difference is greater than -50 is what it's saying. Okay. All right, so this is the wrong way to do it, okay? So let me show you the right way to do this, okay? So that was treating it as independent. Here we have to take into account everyone's original starting weight, okay? And so what's going on here is that if we look at each individual person, does it look like the weight loss pill is working? Adam lost 5 pounds, Bob lost 5 pounds, Carl lost 6, Doug lost 5, and Eric lost 5 pounds. Okay, so it seems like this pill kind of works in helping people lose weight. Maybe only 5 or 6 pounds, but that still seems to be working, okay? What's happening is that if you aggregate them all together and treat them as independent samples, then the average difference of about 5 pounds or 5.2 pounds gets lost among the individual differences, okay? But if we take into account everyone's starting weight and their after weight and their ending weight, then this will work, okay? So what we do is we create a difference column. And then we do before minus after, and we get 5, 5, 6, 5, and 5, okay? And so the mean is going to be 5.2. And then the standard deviation I should just make sure that the mean is 5.2, and the standard deviation is 0.447. And so for a paired t-test, paired data t-test, for paired data t-test, you just create the difference column, and this is now the only column that matters. You only have one column of data that matters. Okay, and your hypotheses change. Okay, your hypothesis, your null hypothesis, is no longer mu1 minus mu2, because we don't care about population 1 and population 2. In fact, it's just the mean difference, the mean of the difference column. Is this mean of the difference column equal to 0? That's going to be the null hypothesis. So this is different. And then the alternative, in our case, we want to know if they are losing weight, meaning the before minus the after should be greater than 0. So is our mean difference greater than 0? Okay. And so our test statistic, we are observing is a difference of 5.2. So our test statistic is going to be d bar, the average of your difference column, divided by the standard error. Okay, and so our standard error is going to be s of the difference column divided by the square root of n. Okay. So this should look familiar, s over the square root of n. Okay, and so our standard error is going to be 0.447 divided by the square root of 1, 2, 3, 4, 5, okay? And again, because there's only one column that matters, now it's just the square root of 5. It's not 10 or anything like that, okay? It's just one column of values, okay? So we're going to have 5.2 divided by 0.447 divided by the square root of 5, which is 0.199999. So that's practically 0.2, okay? Okay, and so my test statistic, 5.2 divided by 0.2, ends up being, now I'm 26 standard deviations away from the mean, which is very far. Almost ridiculously far, okay? And so, you know, now I would look this up in Okay, and so here is 0, and now I'm at 26, and I want to know what's the area over here. Well, we would look this up now in the table with n minus 1 degrees of freedom. So degrees of freedom would be n minus 1. I only have 4 degrees of freedom now. Okay, and I just go and I see, well, how far out is 4 degrees of freedom? The very last values in the table are 4.604 and 8.610. 8.610 corresponds to a tail area of 3 zeros and a 5, and this is 2 zeros and a 5, okay? And here I'm out 26 standard deviations away. So that just means my tail area, whatever it is, it's going to be tiny. So my p-value, the resulting p-value, I don't have an exact value, but I do know for sure it is less than 0.0005. It's even smaller than that. So do I reject or not reject the null? We would reject the null hypothesis. We'd say we reject the null hypothesis. We say our data is unlikely to just be a result of a random chance, and we conclude that the diet pill works. Is this okay? Yeah.
I mean, just going back to chapter 1 where you were talking about like the people measuring social anxiety at a nightclub, like the people who would take these pills would be more likely at that time to be maybe paying attention to their weight. So, do you know what I mean? Like, how do you factor in those things?
Okay, yeah. Yeah, maybe this isn't the best example here, but it's just, this was just, can we have evidence of a difference between here and here?
But in that case, you just avoid like the messiness of that for this and just focus on like the equations and everyone's losing weight, so we don't need to ask ourselves the questions we asked at the beginning.
Right. We should, yeah, for a proper study, we should have a placebo in a different group. Okay, we should have Adam, Bob, Carl, Doug, and Eric. Before and after, they'll get the actual drug, and then there should be another group that got the placebo, and we look at them. Okay, but we would look at, is this group's difference significantly different from 0? Here it is, yes. And then we're going to look at the other group, which is independent of this group, and we'd say, is theirs significantly different from 0? Okay, but yeah.
Okay.
But yeah, effectively, we have to deal with this before and after situation. We can't just treat the befores and afters like that. Okay. I used to have a lab that forced you guys to do this, but then the students said they didn't like it. So I'll just show you how I'm doing this here. Okay. So I could do the same with a t-test of comparing before and after, and I want paired is equal to true, and the alternative is equal to greater. Okay, and so notice over here I'm using before and after, and I had the alternative equal to greater, and our p-value ended up being 43% here. Okay, this is the result of the test there, and we were 0.17 standard deviations away from the mean. Over here, yeah, we end up 26 standard deviations away from the mean. We have 4 degrees of freedom as we calculated, and our p-value ends up being on the order of 10 to the negative 6, so like basically 6 in a million or something like that. Or maybe this is 6 in 10 million? I can't. 6 in a million, I think. So this is about 6 in a million. So it's very, very unlikely for this to happen. Okay. So that's what we get here. All right. So our p-value is on the order of 6 in a million, and so we would say the data that we have here, very unlikely to have been a result of random chance. Okay? And so that's kind of how hypothesis testing works. We look at our data and we say, okay, this is the data we observed. Could it have been a result of random chance under the null hypothesis? Well, we say, well, if the null hypothesis is true, what's the probability we get this data? Okay? If it turns out to be very unlikely for our data to result from random chance, we say, well, I actually have my data, so either it happened from random chance or it didn't happen from random chance, but it happened. So if it's very unlikely to have happened from random chance, we say, well, it probably didn't happen from random chance. I'm going to conclude that my initial assumption, the null hypothesis, is wrong. Okay. On the other hand, if the p-value turns out to be like 0.2 or something like that, where it says it happens by random chance 20% of the time, we say, well, I don't know for sure if it happened by random chance or not, but there's certainly a possibility that it did, so I'm not ready to conclude that my null hypothesis is wrong. Okay, I hope that's okay. We'll have a quiz next week. I do have a few questions kind of like relating the confidence interval to the hypothesis test. And so make sure you're comfortable with, you go over the notes and see like what it says there. And then yeah, you'll have to tell the difference between a paired t-test and a independent t-test, okay? And I think it'll be clear on the problem, but don't forget to do a paired t-test when you're supposed to do a paired t-test, and know that the hypotheses are different for those tests as well. Okay, we'll end here. Have a good week, you guys.